is square threaded screw load calculations. You have seen this car jack is in your car. So it's one of the cheapest piece of equipment that you can lift or lower very heavy load. And it's a very simple calculation. So the information you'll be given for this is a square threaded screw normally used for this application. And it's a single threaded screw, so the lead and pitch is going to be the exact same. So this is the lead of the screw and this is the diameter of the screw. So if you unthread one of these one of the thread from the screw is going to be something like this. So then here, so if you unthread it, that's going to be 2 pi r or pi d. In this case, 2-inch diameters is going to be actually 2 pi. And then the L is given 0.3 lead. So this is theta. We do have to calculate the theta, so we can do for the calculation. So let's do that right away. 2 pi, I found that 2.73 degree. Now the load is going to move up and down, going to act downwards like this, W. And when it's going up, this is stationary piece is screw right here. It has to hold against something. So this nut is stationary in this case, stationary nut. And then when it's going up, the force is going to be coming from the nut in this direction, P force. So the friction is going to act downwards. And the normal force, again, is going to be perpendicular to the surface. It's theta. So it's going to be our normal force. Now we have to do some force resolving stuff. So this P is acting this way. This is theta. So this component will be P cosine theta along this surface. And in this direction, perpendicular surface would be P sine theta. The weight component perpendicular to the surface will be P W cosine theta. And along this surface is going to be W sine theta. So this is everything we have. So while going this thing up, or moving the load up, so this is what you're trying to solve. The first equation you can write, summation of Fx is equal to 0. So we have the plus normal force going upwards. So it's going to be plus minus W cosine theta going downwards. Then also the force, the P sine theta is also going downward too. So P sine theta, everything sum to 0. So then we can write N is equal to W cosine theta plus P sine theta. And then we can also find the friction force, which is mu times N. So then it's going to be mu times W cosine theta plus P sine theta. So this is our equation number 1. Now we can write this summation of Fx is equal to 0. So we have plus P cosine theta acting along the surface. Then minus W sine theta going down along the surface. And then the friction force also going down the surface. So that is equal to 0. So then we can replace that F from equation 1. It's going to be minus mu W cosine theta minus mu P sine theta, everything sum to 0. So we can do P cosine theta minus mu sine theta. P is common. Take everything out to the other side. W sine theta plus mu W cosine theta. Now we plug all these numbers. So cosine theta is now 2.73 degree. Mu, let's say 0.2. sine 2.73 degree is equal to 1000 pounds load times sine 2.73 degree plus mu is 0.2, 1000 pound loads. Assume that it's moving 1000 pounds up and down. In this case, going up, cosine 2.73 degree. So I found this number 0.989, and then also the right side number 247.4. So the value for P I calculated 250 pound approximately when it's going up. Now you're applying, so 250 pound, that's P is actually only 1 inch away. So this knot is applying here, that 250 pounds, that is only 1 inch away in this direction. So the torque coming from that 250 pound would be 250 pounds times 1 inch away. The diameter is 2 inch. This will be exact same as whatever you apply from the hand force, which is Q here, the cranking handle. Q times the distance of that handle is 12 inches. If you do the calculation, then Q, I found that that is only 21 pound. So just to move up 1000 pounds, you only need to apply 21 pounds. Now you have seen in your car example that it's about not so much force when you're trying to lift a wheel of the car. You know, you can think of 1000 pounds. If you say 4000 pounds, one of the wheels, the front will have a little bit more than the rear. But if you lift a rear wheel, it's going to be about front wheel for a 3000 pound car, it's going to be about 1000. So you'll feel about this much using a 12-inch handle Jackscrew like that. Not a whole lot of force you have to apply to leave that much amount of force. Now lowering it, as you know, it's going to cost you even less than that. So let me show you that calculation. When you lower this Jackscrew, the force direction changes. So this nut now is going to apply in a lowering condition, pull this way. The weight is not going to change its direction. It's always still the same. Theta, we already did that calculation. So now this is the theta. So the normal force, again, that doesn't change direction either. Still the same. The force component and also the weight component, their amount is still the same, but the force changes, so its direction is going to change. So W cosine theta resolve in this direction, and then along this surface is going to be W sine theta. The P along this surface would be P cosine theta, and it's going to act now downwards. And then the perpendicular to the surface is going to be P sine theta. Now the normal force is going to change because now it's pulled. So it's going to be actually N is equal to the weight component to the perpendicular to the surface minus that sine theta, P sine theta. Is going to reduce a little bit. So F is going to be now then mu times normal force, which is W cosine theta minus P sine theta from. So this is my equation number 1. If you write summation of Fx, that's going to change as well. Now the friction force direction changes to the upward direction. So everything else is going down now. So now it's going to be minus P cosine theta, which was plus before. It's going downward now. Then plus F, that's the only thing going up. But the weight component also be the weight component also going downward, which is W sine theta. I think this is, I mean W, not P. So that's W sine theta, the weight component along this surface. So here, so that's the situation. Everything is equal to 0 minus P cosine theta. Now we're going to plug that value of F from equation 1, in this case going down. So it's going to be mu cosine theta minus P sine theta minus W sine theta. Everything sum to 0. If you rearrange this and plug so it's going to be W P, if you take P common, so minus sine theta minus cosine theta is equal to W sine theta minus mu W cosine theta. If you plug all these numbers, I found that P would be 84 is equal to minus 152. This is also minus. So then the value of P, I found 151 pounds. Now 151 pounds acting right here downwards times the distance of, so now going down, so 151 pounds time, it is 1 inch away from the screw. That has to come from the handle force, which is 12 inch away from the center of the rotation. So the Q, when it's going down, is going to be about 13 pounds. So only 13-pound force you have to apply to lower the car down. Very interesting.